How do scientists study the smallest building blocks of the universe? They use particle accelerators like the cyclotron. This device uses electromagnetic fields to accelerate charged particles to incredibly high speeds, enabling breakthroughs in medicine and research. Beyond pure research, cyclotrons are essential in modern medicine. They produce short-lived radioactive isotopes used in PET scans to detect cancer, and they power proton therapy to treat tumors with pinpoint precision. The heart of the cyclotron consists of two D-shaped hollow metal electrodes called Ds. These Ds are placed inside a vacuum chamber to prevent particles from colliding with their molecules during acceleration. A powerful electromagnet creates a uniform magnetic field perpendicular to the plane of the Ds. This magnetic field does not speed the particles up, but it provides the centripetal force needed to bend their path into a circle. An alternating high-frequency voltage is applied across the gap. This creates an electric field that switches direction. Every time a particle crosses the gap, it receives an electrical push, increasing its kinetic energy and speed. The physics relies on the Lorentz force. When a charge Q moves with velocity v in a magnetic field B, it experiences a force perpendicular to its motion. This force acts as the centripetal force, mv²/r. As the particle gains speed in the gap, the magnetic field forces it into a larger circle. This results in a spiral path. Even though the speed increases, the time taken to complete a half-circle remains constant. Crucially, the frequency of the circular motion is independent of the particle's speed. This allows the alternating voltage to stay at a fixed frequency, perfectly synchronized with the particle's arrival at the gap every single time. Let's calculate the frequency required for a proton in a 1.5 Tesla field. By plugging in the charge and mass of a proton, we can determine exactly how fast the electric field must oscillate to maintain synchronization. The result is approximately 23 million cycles per second, or 23 MHz. This falls within the radio frequency range, which is why the power supply for a cyclotron is often called an RF oscillator. The maximum kinetic energy a particle can reach depends on the strength of the magnetic field and the radius of the Ds. The larger the cyclotron, the faster the particles can go before they are extracted. For a cyclotron with a radius of 0.5 meters and a 1.5 Tesla field, the exit velocity would be roughly 72 million meters per second. That is nearly 24% of the speed of light. Once the particles reach the outer edge, a negatively charged deflector plate pulls them out of their circular orbit. They are then directed toward a target, such as a metal foil or a biological sample. A standard cyclotron has limits. As particles approach the speed of light, their mass increases due to relativity. This causes them to fall out of step with the constant frequency of the electric field. To solve the relativity problem, synchrocyclotrons adjust the frequency of the electric field to match the slowing pace of the heavier, faster particles, allowing them to reach even higher energy levels. Remember, the magnetic field provides the steering, while the electric field provides the speed. The synchronization of the two is what makes the cyclotron a masterpiece of classical physics and engineering. Here is a quick check: which field is responsible for increasing the speed of the particle? If you chose the electric field, you are correct. The magnetic field only changes the direction of motion. From exploring the atom to saving lives in hospitals, the cyclotron remains a cornerstone of modern science. Thank you for exploring the physics of acceleration with us. Generated by Vision Solve AI.